Math 2414, Surface Area of Revolution, Video 2. Formulas based on independent variables and axis of rotation. All I mean by based on independent variables is whether you have a function of x or a function of y. So we have two different characteristics that will define the integral that we set up. Number one is whether we have y equals a function of x or x equals a function of y. And by the way, for some graphs, you can view them both as functions of x and functions of y. Everybody should know the vertical line test. If you pass it, you're a function of x. A lot of you don't know that there's also a horizontal line test, that if a horizontal line can only cross a graph once, then that is a function of y. So you may be given a function of x, but have to turn it into a function of y by solving for x. But I digress. Your function is either going to be y equals a function of x or x equals a function of y. And you can often manipulate from one to the other. And then your axis of rotation, for the sake of simplicity, is just going to be the x-axis or the y-axis. It is possible to extend this concept to rotating around other vertical lines and horizontal lines. You would simply translate the function left, right, up, or down so that the axis of rotation would land on the x-axis or y-axis and then proceed accordingly. So what did we do last time? Well, last time we set up a formula for rotating the graph of a function around the x-axis. And just for clarity, let's say that we have a graph that can be viewed both as a function of x and as a function of y. Y equals a function of x, and we'll say it goes from a to b. But we could also think of this as x equals a function of y, so we'll say x equals g of y from c to d. And then we'll consider rotating around both axes. Now, in the first video, we developed the formulas for rotating around the x-axis, so let's summarize those. The lateral surface area, when you're rotating the graph of y equals f of x around the x-axis, was the integral from a to b of 2 pi f of x times the square root of 1 plus the square of the derivative of f of x dx. But if we were rotating around the x-axis and we had a function of y, then the lateral surface area was the integral from c to d, dy. I'll get to the dy in a second. Doing a dy integral, basically. It was 2 pi, but instead of f of x, it was just y. And then the square root of 1 plus the square of the derivative, g prime of y, dy. However, if we were to rotate around the y-axis, everything would pretty much just be reversed. If we had a function of y and we were rotating around the y-axis, it would look almost just like a function of x rotating around the x-axis. But instead of everything in x's, it would be in y's. So our lateral surface area would be the integral from c to d of 2 pi g of y times the square root of 1 plus the square of the derivative of g of y dy. And if we had a function of x, a graph of a function of x that was being rotated around the y-axis, that would be analogous to a graph of a function of y rotating around the x-axis. So it would be this, but it would be all x's instead of y's. And our lateral surface area would be the integral from a to b of 2 pi x square root of 1 plus the square of the derivative of f of x dx. Now, I'm not going to lie to you. The first time I saw this, I got these mixed up all the time. How come sometimes there's a function in front, sometimes there's not? How do I know when to put a letter and when to put a function? And how do I know which letter to put or which function to put? Well, really, everything is dictated by whether you're doing a dx integral or a dy integral. So let's start there. If your function is a function of x, let's get a better marker than that one. If your function is a function of x, then you are going to do a dx integral. So there's the consistency there. And similarly, if your function is a function of y, then you are going to do a dy integral. So let's get that out of the way right now. Function of x, dx integral, function of y, dy integral. Notice under the square roots, the function's independent variable matches the variable in the differential. So if you're doing a dx integral, you need the derivative of a function of x on the inside. And if you're doing a dy integral, then you need the derivative of a function of y on the inside. As far as what goes in front, the short answer to what goes in front, whether it's f of x, y, x, or g of y, the thing that goes in front is the opposite of the variable of the axis of rotation. What do I mean by that? Well, when you rotate around the x-axis, remember that we talked about the radius, which was right here. Well, when you're rotating around the x-axis and measuring from the x-axis to the curve, that's the y-coordinate, which is also f of x in this case. So when you're rotating around the x-axis, your radius is y. So let me restate what I said earlier. What goes in front? In other words, what's the radius? The thing in front is the radius, regardless of which direction you're rotating. Where the radius is the distance from the axis of rotation to the curve. So if you're going around the x-axis, your radius is the distance from the x-axis to the curve, which is the y-coordinate. But if you're a function of x, then that's the same as the function of x. And if you notice, both of these are the radius from the x-axis to the curve. So how do you know which one to use? How do I know when to use f of x as the radius as opposed to y? That's dictated by your differential. If you're doing a dy integral, your radius needs to be something with a y in it. In that case, it is y. But if you're doing a dx integral, then it needs to be something with an x in it. In this case, f of x. But if we were going around the y-axis, choose this color green, I think it will show. If you're going around the y-axis, then your radius is the distance from the axis of rotation to the curve. Well, in that case, the radius is x, or g of y, if you have a function of y. So when we're going around the y-axis, my radius needs to be either x or g of y. Which one? That depends on the differential. If I have dx, I need an x here. If I have a dy, I need g of y. I'm sure there are other gimmicky ways to remember how to set these up. In fact, I can show you right now. By collapsing some of these things down. Remember that the square root of 1 plus the square of the derivative times dx dy all came from ds. ds is either the square root of 1 plus the square of the derivative of f times d of dx, or the square root of 1 plus the square of the derivative of g of y dy. But either way, I can collapse it down to ds. When you're going around the x-axis, the thing here is f of x or y. If you're going around the y-axis, your surface area is the integral of 2 pi, still ds, but when you're going around the y-axis, your radius is either x or g of y, which are equal, we'll call it x. So this is probably the most compact way I can recommend for remembering these formulas, is that the surface area is the integral of 2 pi y ds when you go around the x-axis, or 2 pi x ds when you go around the y-axis. How do you know whether to unpackage ds into the square root of 1 plus f prime squared dx, or the square root of 1 plus g prime of y squared dy? How How do you know which one to unpackage it into? It just depends upon whether you're a function of x or a function of y. Just make sure that before you integrate, everything is in terms of the same variable. If you're doing dx, everything should be x's. So if you have a y, replace it with f of x. If you're doing dy, everything should be in terms of y's. So if you have an x, replace it with g of y. Sounds like a lot to keep up with, and I'm not going to lie, it sort of is. But you're in calculus 2, and the math gets challenging. The rest of the videos are just going to be working some examples. I have 1, 2, 3, 4, 5 examples in store. Some are much easier than others, as you will discover.